Hi everyone. For now, this is my last video on adders. In particular, I want to talk about how we can create computer circuits for adding two binary numbers like this. If you haven't seen the earlier videos on half adders and full adders, you're in the wrong place, sorry. So if you have seen those videos or you understand how half adders and full adders work, then carry on. So what we want to do is we want to figure out how to compute this sum using the half adder circuit that we created in the last video. So what I'm going to point out again and again is if we're trying to create a circuit that can add two numbers of any length, then we have to recognize that this full adder that we've created, that it itself is based on half adders, this full adder circuit, it can only add one column of bits at a time. So what we're going to do in our circuit is we're going to basically split up the computation into one column at a time, one bit at a time, so that we can efficiently create blocks. We can efficiently reuse our basic building blocks, the full adders, again and again. Now, based on that, I'm going to keep pointing out what the carry-in is, what the x and y are, because those are the inputs we'll need to keep in mind in order to use the full adder. So let's start with the problem here. Well, quite clearly 7 and 5 is 12. You can verify this is 7, this is 5. So what we want to do is I will focus one column at a time. The first column, it has a carry-in of 0. In effect, we just haven't added anything that could be carried, so we have a carry-in of 0 to start. X is 1, y is 1. So, well, you know what the sum should be. It's 1 plus 1, that's 2, so that would be 1, 0 in binary. Because we can't write 1, 0 in the same bits, then we write just the 0 as the sum, and we'll carry over the 1. So what this looks like using a full adder is, I will draw it FA, full adder. The full adder will take in a carry-in of 0. It will take in x is equal to 1. It will take in y is equal to 1, and the sum it produces is 0, and I'm going to send this rightwards, you'll see why. The carry out it produces is 1. So that is the first bit, the first column done. Let's move on to the next column. So in the next column, what we see is we have a carry-in of 1. Well, you might note the carry-out from the last column, it's the carry-in of the new column. And we're going to add 1 plus 1. Again, if you add 0, nothing changes. Again, you're going to have a sum of 1, a carry-out of 1. Sorry, sum of 0, carry-out of 1. So in a full adder, well, notice the thing I just said. So the carry-in for this column is the carry-out of the last column. So I'm literally just going to take this and plunk it in here into the next full adder. This is our new carry-in, the same as the carry-out for the last column. The x and y in this case are 1 and 0. So 1 and 0. We get out an output of 0. Okay? That's our second column done. Move on to the next one. Again, we had a carry out of 1 over here. It becomes the carry in of the next full adder, and you can see where this is going. So I'm not gonna bore you with all the details. You can see x and y are 1 and 1. The output in this case is 1 plus 1 plus 1, we get a 3. So 3 is 1, 1. You can only put 1 bit here, so you just put 1 over here, and the remainder, the carry out, goes over here. So we get a sum of 1 and a carry out of 1. Do this one last time. So the carry out becomes the carry in. We get another full adder. This time you can see x and y are 0 and 0, 0 and 0. And we have 1 plus 0 plus 0, so that is the sum 1, and the carry out is 0. So I'll just put in a sum of 1, oops, sum of 1, and carry out of 0. This is what we call a ripple carry adder. So the reason we call it a ripple carry adder is that you have, the carry out, it is kind of rippling from one to the other. So just like a ripple extends outwards, affects every other part of a pond, this ripple, this carry out, affects every other part of the circuit. You'll note that the outputs that we get out, well, clearly this is 12, so we computed the correct output. You'll note that the outputs that we get out, they're in reverse order. So this is the rightmost digit, it's the rightmost bit or digit, and this is the leftmost bit or digit. Even though this is left, that's right. So you just flip the order of the outputs that you get out to read your sum. Of course, you could keep extending this on and on and on as much as you want, and that's how you could add numbers, any binary numbers of arbitrary length. They don't need to just be length 4, so you could have a dot 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 to signal that the circuit could go on and on and on. Concept isn't very hard to grasp. Just the issue with this is it's a very slow circuit. Because if you could think about it, over here, this full adder can't do its work until it receives this input. To receive this input, it has to wait for this full adder to do its work. For this full adder to do its work, it has to receive this input. To receive that input, it has to wait for this full adder to do its work. And you go on and on. So this full adder is basically just waiting for 3 other full adders to do their work before it can do anything. As you can see, if you keep on adding numbers, these days we're often, if you've ever coded something, you've done work with doubles or floats, 32-bit or 64-bit numbers. So it's like if you're the 64th or 63rd adder in the chain, you gotta wait for all of these adders before you to get something done before you can do anything. So most of the circuit is just sitting there uselessly for most of the time. So that's why this ripple carry adder, it doesn't get used very often in real-life production systems. There's a lot of optimizations that you can do to this basic circuit. However, this one is easiest to understand. The other ones are very complicated. You have to keep diving into the details of how the full adders work and how you connect them. But just to give you a hint that I will not explain in any more depth, what you're usually doing is, if you're the adder over here, you might compute one output and carry if the carry-in was a 1, you might compute another if the carry-in was a 0. So the optimized circuits, what they will do is they will run this full adder once, assuming the carry is a 0. They will run it another time, assuming it's a 1. And that way you have some results. You can select which one you actually need based on what the carry turns out to be once the ripple has gone through. But it allows you to do more parallel work, so that this full adder isn't just sitting idly the entire time. I hope that is an interesting introduction to ripple carry adders. If you're interested in more optimization, just search up adder circuits on Wikipedia. You'll see lots of optimizations there. But for now, that is the mini-series on adders.